temperature and energy, this links the macroscopic scale big effects to the microscopic scale. Now, in the starter, which you definitely did, I asked you to remember some things and do some things. If you've not done those things, this will be way over your head. So if you skip the starter, stop being lazy, do the starter and come back and then watch the video. You know, having done that starter now, that internal energy is the sum of randomly distributed kinetic and potential energies of the particles. And because there is no force acting between those particles in an ideal gas, that means there's no potential energy. If an ideal gas possesses no potential energy, then all of the energy it contains has to be kinetic. I've done that over 2 or 3 videos now. Ask me if you want it clarifying in a different way. If you've done the starter, you'll also realise that the product of a pressure and a volume has the unit of joules. Obviously the metres all cancel off and you get Newton meters, which is a joule, force times distance. And that enables us to link it to internal energy, and therefore specifically link it to the kinetic energy that those particles possess. Again, there's no derivations involved here because it involves statistical mechanics, which is a 2nd or 3rd year degree piece of physics. Here, we're just going to look at the outcome of the final end result equations that are useful to us at A-level. We introduce an idea of a mean translational kinetic energy. That's a very, very posh way of saying the average K that a particle has. Technical language to use here is the mean translational kinetic energy, and it's directly proportional to temperature. Higher temperature, more kinetic energy. When we reach absolute zero, remember in the last video, absolute zero is where the kinetic energy goes to zero as well. So it has to be directly proportional. It's a straight line through the origin, provided we use temperature, absolute temperature in Kelvin. The mean translational kinetic energy of one molecule, or the kinetic energy of a single molecule of gas, is 3/2 kBt, where kB again is that Boltzmann constant from the ideal gas equation. If I want to know the speed of a molecule, I can set this value, I can set the mean translational kinetic energy of a particle equal to 1/2 mv squared, and I can work out speed of a single molecule of gas. Particles in a gas all travel at different speeds in different directions, and just trust me, the distribution of these speeds follows a different type of curve and therefore requires a slightly different type of statistic in order to calculate an average. The root mean square speed is a technique for averaging these non-normal distributions. And whenever you're talking about particles in a gas, refer to their speed as the root mean square speed. I've written a simple question here and I've kept it generic. Find the root mean squared speed of a gas molecule given the temperature and the mass of the molecule m. The reason why I've chosen this is because it's also the most common type of calculation that I'll get you to do in an exam, and you'll see that it's actually incredibly easy. What might be useful for you to do with this is to follow along with example 4 and 5 in the back of the book. By all means, write this in the additional space that you have in the 5.3 book. If I want to find the root mean squared speed of a gas molecule with mass m at temperature T, I need to first start out with finding the kinetic energy. E equals 3/2 kBt. The kinetic energy of a single particle of gas is equal to 3/2 times Boltzmann's constant times the temperature. That equation is brilliant. Because E is kinetic energy is equal to 1/2 mv squared. So I can then set that equal to 1/2 mv squared. In this case, the V is the root mean squared speed. I'm really annoyed with the C bar. It's just needless. If I called that C bar V, there would be no confusion, but for some reason they just put it in there. It really gets me going. It doesn't matter whether you want to evaluate it and plug it into a calculator and find C bar that way, or whether you want to rearrange it and put all the numbers in one. Whatever method that you find easiest is fine, but I just thought that I'd show you this to demonstrate it's actually quite easy. If I know the temperature of a gas, I instantly know the kinetic energy of a molecule, because E equals 2 over 2 kBt. And if I know something's kinetic energy, then I know its speed, because a half of V squared. Except annoyingly, they call V c bar, just overcomplicating perfectly decent physics. We're able to find the average speed of a molecule in a gas, just given the temperature and its mass. In a gas, the distribution of speeds is not a normal distribution. It's not what you're used to dealing with in everyday life. Particles in a gas all travel at different speeds in different directions. The distribution of these speeds follows a different type of curve and therefore requires a slightly different type of statistic in order to calculate an average. Energy follows the same distribution as well, kinetic energy. This distribution, the Maxwell-Boltzmann distribution, you need to know how to sketch it and be aware of it. We tend to get more molecules down here at lower speeds, but it doesn't mean that molecules can't travel very fast. At an increasing temperature, more molecules move at higher speeds. However, again, that distribution is not even. For any gas, there will always be a small number of particles that possess very, very high energies. There is a finite probability at any temperature that the particles will have a very, very high speed, much, much higher than the RMS. The chance of it doing so is unlikely, but as you increase the temperature, that probability increases. There are various standard answers that come up across Unit 5 and 6 which rely on this fact. The root mean square speed is a technique for averaging these non-normal distributions. So when I refer to the root mean square speed, it's just the average speed, but for a very specific type of statistical distribution. All you need to know about that are the words, nothing else. No detail is required, just using equations. There is an alternative equation for finding the root mean squared speed, or for finding the number of particles when you're not given temperature, but you're given, say, pressure and volume. So that equation is PV equals 1/3 capital N M c bar squared. This equation is really rarely used, maybe once or twice in our questions, and I think I've only seen it used once in an exam for 2 marks. So I don't like to make a big deal of it, but it is handy if you want to find, say, capital N number of particles. You've just got to remember that in this equation, PV, those are the large scale states of the gas, pressure and volume. Capital N, it's always a capital when it's going to be a really massive number. That is the number of individual molecules in the gas. M is the mass of just one of those molecules, and that's really important, not the mass of the whole gas, just of one of the molecules. So that's going to be really small, so they're going to end up balancing each other out to give the root mean squared speed, which would be probably a few hundred meters per second. This is the one with a typo in the formula book. Keep a lookout for this. The typo has the bar across the c and the squared, and that really confuses people. It's actually a genuine error, and it's not printed in every version of the formula book. So just keep an eye out. That bar should just be across the c. Don't get confused if it is across the squared though. That is a typo. Just imagine it's a v for velocity and square root it as normal in order to evaluate that. I'm going to say no more about this equation other than there's a derivation task in the book that uses it to derive the more common E equals 3 over 2 kBt. You can see how setting that PV term equal to the ideal gas equations PV equals nRT, we can just cancel off a bunch of things, and then that comes out with mc bar squared, which is double the kinetic energy of a particle. I think the derivation is fairly self-explanatory in the book, but I think it's really rare that you would ever have to use both this equation and that derivation. For completeness, we've included it. Just while we're here, I'm going to take a really brief look at these standard answers so that you can appreciate how they take these large-scale properties and relate them down to the small-scale properties. Again, like I said in the previous video, these are questions that come up all the time and we are giving you the answer. I can guarantee, and I will put my month's wages on it if you like, that one of these answers will come up in the final exam. And if you've learnt it, you can bank marks there. If you've not learnt it, you'll be floundering. That's the point in these standard answers. In this, you're asked to explain why the force exerted on the walls increases using the kinetic theory of gas. It's a nice standard answer, guys. We've instantly made that link between the giant scale temperature and the microscopic scale kinetic energy. Where do people go wrong with this standard answer? They often forget that there's actually two elements here. Most people will say temperature goes up, speed goes up. That's the mark that everyone gets. Most people will then say if the speed goes up, the rate of change of momentum will increase, and so the force will increase by Newton's second law. You've got 3 marks, but it'll be worth 4. The 4th mark is the forgotten one, the one that comes from that statement there. Not only are the particles moving faster, if particles are moving faster, there'll be more frequent collisions, and that word frequent is important because they have to collide more in a given unit of time. So more frequent collisions. That is the 4th mark that people always forget. There are more collisions going on, and so that force not only will increase because of the change of momentum, it will increase anyway because there's more collisions per unit time. Another standard answer, why does the volume increase with temperature? In order to keep pressure constant. As the temperature increases, the speed increases. That's why everyone gets the mark, by the way, because it comes up in every single standard answer. It's one of those things just to say, whenever you've got an increase in temperature, you'll also have an increase in speed or kinetic energy. As a result, collisions are more frequent. Hey, this is the same as the last standard answer. Yeah, they're all the same, except for the end. So learn it. So actually, these first 3 bullet points are the exact same. So now what we have to do in the second half of this standard answer is the hard bit. We have to explain why that means the volume must increase so that the pressure is constant. In order to keep the pressure constant when those particles are moving at higher speeds, we need to try and reduce the number of collisions. So the first additional bullet point in this standard answer states that fewer collisions per unit time are required. We want to reduce the frequency of collisions. How do we achieve this? Well, if we increase the volume, we will increase the travel time, the distance between collisions. So if we increase the volume, if I have a bigger space, the particles will simply have further to travel between those collisions, thus reducing the rate of collisions. So compressing a gas, that means reducing the volume. Why is it likely that when I do that, the temperature will go up? Well, it's fairly simple. If I compress a gas, I need to do work because there's a pressure acting on the outside of my container. If I want to compress it, I have to provide a force, and that acts over a distance. So work is done when I compress a gas. I'm putting energy into that system. If I'm doing work on the gas and I'm putting energy in, that will raise the internal energy of that gas. So the kinetic energy will increase, and so the absolute temperature must increase as well, because temperature and kinetic energy are directly proportional. Notice that logical chain of, if I do this, then I do this, if I do that, then I do that. Learn these standard answers. If you have questions, again, I could try and explain it in a different way, perhaps by email, just ask. Explain why the absolute temperature of a gas tends to fall when it's allowed to expand. It's the same but in reverse. If a gas wants to expand, i.e. it wants to push the walls of its container outwards, it's going to be applying that force and that pressure over a distance. So the gas now is going to do work on its surroundings. By conservation of energy, when a gas does work, it loses internal energy, and therefore losing internal energy will lead to a decrease in its absolute temperature. It makes sense when you know how, but if you didn't know these standard answers, if you hadn't committed time to learning them, memorising them, this could very quickly cause you to become stuck. And usually, in my experience, when students try and wing it, It's the starting point that they forget. And so they end up getting 0 marks because they can't remember it's to do with work done. Don't think that we can't tell when students try to make up the answers. We've been teaching for 20 years combined, myself and Gary. We have lots of experience. Gary is a chief examiner and marks 400 papers a year, maybe even more. We can tell the difference between a student that learns the standard answers and a student that is winging it. Don't think that we can't. Make sure you learn these standard answers. The standard answers listed there, use that formula as a link between the macroscopic and the microscopic, between the big and small states of that gas. They talk about pressure and link pressure directly to the average kinetic energy of one molecule, of one particle in that gas. Same for temperature, same for volume. You can now link those giant properties to the microscopic properties in that gas. That is done using equations, but it's also done using words. And you have to read and get to know those standard answers. They show you how this is done. As for today, now on Thursday, I recommend you get to the back of the book and practice putting all of these equations together. There's a lot in ideal gas, as I said right at the beginning of the week. There's a lot to understand. And in my opinion, whilst you could cling to the formula sheet here, holding on for dear life and just hoping that all the numbers work out okay and you get it right, it's not as good a strategy as actually learning and understanding what these equations mean. For example, PV equals nRT, great. N is moles, moles is mass over nR, it's the number of particles times Avogadro's constant. Right, that's the level of understanding that you should have. T has to always be an absolute temperature in Kelvin, otherwise it won't work. That is the number one place where people go wrong, by the way, is they forget to convert their temperature to Kelvin. Everywhere you see a capital T, here, here, that is an absolute temperature in Kelvin. So the conversion between Celsius and Kelvin is a big deal here as well. This capital N is the number of individual molecules, whereas little n is the number of moles. That's important detail to understand as well. C bar squared is the root mean squared speed squared. So if you want to find the actual speed, you need to get rid of that square so that you just free up that C bar. I wish it was just a V, I honestly do, but it's not. Here we've got the gas constant, 8.31. Here we have the Boltzmann constant, which is tiny. So those two constants are very different as well. Make sure you use the right one in the right place. And finally, an important point, this is the predominant method for calculating the average speed of a particle. This is very rarely used. It is imperative that you practice using all of these equations, spotting them in the right place. And I know that today, on your very first day, you will not feel great about it. I'm going to tell you, you will feel like there's a lot to take on board. And you are absolutely right, because there is. So allow yourself time, allow yourself a few days, do some practice on it, go away and take a break and come back to it, consolidate. And by all means, if you're watching this on YouTube, look at the suggestions down the side. Is there any other places that explain this? Don't get too confused and certainly don't use their terminology, but it might just help slot things into place a little bit better. All of these equations will be so useful to you over the coming weeks and months. Make sure that you learn them, and if nothing else, the one thing that you must take home is that PV equals nRT.